Okay, so now to talk about the real zeros of polynomials. Now, we've already really talked about the zeros of polynomials, or at least the real zeros of polynomials, and those were the x-intercepts of the polynomial, basically where the graph crossed the x-axis. We also talked about this as an algebraic relationship, although we didn't really investigate it, and that's what we're going to do now. So if you remember, just kind of like the algebraic relationship, the zeros are going to be the values of x that satisfy the relationship when f of x is going to be equal to 0. Now, in this warm-up, you can see I don't have any f of x, I have y, but just remember it's, f of x and y are really kind of interchangeable, just depending if we're talking about equations or functions here. So we're going to look for the x values when y is equal to 0. Now, for solving quadratics, I wanted to pick, quadratic equations are polynomials, so we wanted to kind of look at some ones where we have multiple different ways to solve them. Now, in this first example, here we have a quadratic trinomial, and in Algebra 2, we talked about, the quickest way to solve a quadratic is usually to try to factor it. Now, you don't have to factor it. You could, use completing the square. You could use quadratic formula, but I think in this course, it's very important that you are very comfortable with factoring, because what you'll see for the rest of this lesson, we're going to be doing a lot of factoring. Now, this is not a factoring tutorial, but let's just kind of go through a quick little review of how I would factor this, or at least to check to make sure it's factorable. So sometimes we can use what we call like this little diamond method, and you take the last term, the constant, and you can write it up here, and you can take the coefficient of the middle term and write in there. And basically, if you're factoring, what you're doing is you're looking for two numbers that multiply to give you -6, but then add to give you a +1. And if you need help, you can list out all the factors. But the more and more practice you get, the quicker and quicker this is going to be, and you can see that those two factors are going to be 3 and 2. Now again, when solving this, we're looking for the values of x that are going to be when y is equal to 0. So what we're going to do is we're going to place y with a 0, and then I'm going to use this as a factored form. I'm going to use these values 3 and -2, so I'll have x plus 3. Sorry, let's zoom in here. X plus 3, and then times x minus 2. And then if you ever wonder, like, did I factor that correctly, check, go back to applying FOIL or distributive property, make sure it's correct. 3 times -2 is -6. 3 plus -2 is going to give you a +1. So that works, because obviously when you multiply x times x, you get x squared, and those two terms are going to add up to give you 1x. Now what we need to do is we have the product of an expression equal to 0. And if you looked around, you kind of cheated, you'd see we wrote down the 0 product property. So hopefully that maybe recalls some things that you previously learned. I've noticed a lot of people just kind of forget the name of this property, and they immediately just kind of know what to do, and they automatically, so let's just set them both equal to 0 now, and then we can go ahead and solve. Now, what's nice about the 0 product property, which again I'll talk more about in a second, is that now since you have applied this product equal to 0 for each expression now equal to 0, now you can just solve using inverse operations. So we have x equals -3, and then add a 2 to both sides, and then x equals 2. Okay, so now you can see those are our two solutions. The big thing we want to do is don't try to add the 6 to the other side and then take the square root. That's not going to get anywhere, and I'll show in the next example, the issue with that. So the next example is kind of like a little bit, might kind of seem obvious here, but you notice that this is exactly what I wrote down here, and I kind of have a reason for this, and we'll talk about it. But if you notice that this is already set equal to 0, nice, it's already in factored form, and if I'm just asked to solve it, then, well, wow, I don't really need to do anything else. I could, apply the 0 product property, set them both equal to 0, but I already did that. So let's just write down the solutions. X equals -3, and x equals 2. Kind of quick to solve that, right? So the point that I was getting to, where a lot of students will make some mistakes here, is on a problem like this, where they have an x on both sides. They see the quadratic, and they're like, oh, okay, well, let's get rid of the square root. So they square root both sides, and you get x equals square root of 4 is 2. But you can't leave the square root. So then you have square root of x. Now, we didn't get anywhere closer with solving for x in this case. So we're kind of not really anywhere near being able to solve, and dividing by x on both sides is not going to isolate the x any more than any further than what we can do. We're kind of stuck in this case. So it's very important when we have x's that are not like terms, like in this case an x squared and an x, we don't want to apply our inverse operations like we did with linear equations. we need to think about factoring as an opportunity. Or you could use quadratic formula. But either way, before you even use quadratic formula or factoring, you have to have it set equal to 0, right? Because that's what we're trying to do. We're trying to solve it. So we want to make sure it's set equal to 0. So in this case, what I'm going to do is I'm going to take the equation x squared minus 4x, and I'm going to set it equal to 0. So to do that, I am going to subtract the 4x on both sides. So therefore, now I have x squared minus 4x equals 0. Now I could use quadratic formula if I wanted to, or I can look into factoring this. Now I notice this is not a trinomial, so I can't use my factoring technique I did over here. But if you remember, if we had two terms, we either want to look for like difference of two squares, which this is close, but not exactly, or we want to look for factoring out a GCF. And I can factor out a GCF. In this case, they both these terms share an x. So if I factor out an x, I'm going to be left with x minus 4 equals 0. Now I can use the 0 product property again. So I'd have x equals 0 and x minus 4 equals 0. Therefore, x equals 4. Okay, very nice. Now, in the next example, again, we're left with, hey, this is already in the factored form. Like the zero's on the other side, but who really cares where the, what the orientation is? We can still apply the 0 product property in this case, and we can just write down the answers. Now, you might be questioning, like, why would I go through giving you basically the answer after kind of doing the work? Well, it kind of comes into the question here that I wanted to ask is, the obvious question, which ones are easier to solve? Well, of course, it's easier when things are factored, right? And what methods or properties were useful. And if you remember in quadratics, a lot of students don't remember the name. Sometimes they look ahead into the notes and say, oh, 0 product property, inverse operations. These were helpful properties for us to be able to solve quadratics. Well, guess what? When we get to polynomials with higher degrees, we're going to be applying these same techniques. Now, the problem is we're not always going to have trinomials. So we're not always going to be able to factor something like this. It's not always going to be able to factor out a GCF. We're not going to have quadratics anymore. We're going to have higher power polynomials, so we're not going to be able to use the quadratic formula. Now, there's a lot of different techniques, but the main important thing I want for you to understand is we want to get to this point. If we can get our equations in the factored form, or if we're given an equation in factored form, it's really easy for us to find those real zeros, right? So that's kind of a benefit. We like this. This is good. And that's what we're going to want to do for all of the equations, that we have when we're trying to find zeros. All right, so if you weren't familiar with the 0 product property, you kind of forgot it. Let's just kind of cover it again real quick. The 0 product property basically states if you have the product, now again, this is A times B, right? Or any product here. When you have the product of two numbers, terms, expressions that are set equal to 0, then A or B then A or B must equal 0, right? So again, if you have a number times some other number and it's equal to 0, basically it's saying one of these numbers has to be 0. Both of them could be to 0, or one of them though has to be equal to 0. So therefore, we'd set A equals 0 or B equals 0. Now again, this doesn't have to be just like random variables. You could have like A times B squared like equals 0. Again, either A equals 0 or B squared equals 0. And then the other thing is you could also have like some expressions like, not X, let's keep this with A's and B's. We could also have like A minus 3 times B plus 1 equals 0. Well, just like we said this has to equal 0 or this has to equal 0, in the same respect, if A minus 3 times B plus 1 is equal to 0, that means either the expression A minus 3 is equal to 0 or B plus 1 is equal to 0. And that's why we set them both equal to 0, because we want to say, well, what numbers then make A minus 3 equal to 0? Well, obviously you can just say 3 because you plug 3 in, you get 0. Or you could add a 3 to both sides and say, okay, A has to equal 3, and then you say B plus 1 equals 0. So B equals -1. But please remember, this only works, the 0 product property only works when you have your expression set equal to 0 and it's the product, right? So A plus B equals 0, no 0 product property. Or if I have A times B equals 1, there's no 1 product property. It only works when the product is equal to 0 or when you have the product of them, not any addition or subtraction, okay? Let's go ahead and just review again the real zeros. Remember the real zeros, we already talked about this, f of x, or we could say y is equal to 0. The real zeros, again, is the x-intercept of f of x, okay? Multiplicity, we talked about that previously. Again, multiplicity is going to be like the behavior, so we know that it's going to cross, right? So it could cross or it could bounce. So if we have some kind of polynomial, if it crosses, that means the multiplicity is odd. So let's say here's A and here's B. Okay, so if we wrote these as factors, so we could say like x, plus A to the n, and then this one be like x minus B to the, I'm using m here. So in this case, you could say that m is, since it's crossing, m is odd. And in this case, you could say m is even. And where it crosses at x equals b, and this one crosses at x equals a. So whatever these zeros, it could be represented by any numbers. That actually is going to be a negative a. We're just pretending it's some answer, some number, right? So as long as you have something written in product form, right? So when we're talking about multiplicities and zeros, we got to have them multiplied by each other. So when we have them multiplied by each other and they're raised to a power, that's going to be your multiplicity. These two zeros both have a multiplicity of 1. That means they cross at the x-axis, okay? So that's important. And then the last thing is all polynomials can be written as a linear factorization. So kind of going back to our last example here, when you have a quadratic, any polynomial, doesn't matter what it is, y equals x squared, plus x minus 6. This can be rewritten as a product of its factors. And if you remember from the warm-up, that's why it's so important. Because if we can figure out what the product of the linear factors are, we can find the zeros very, very quickly, right? So or even if I had, y equals, here's another quadratic. And I'm going to do polynomials here coming up, so I'm not going to, I'm just right now I'm focusing on linear factorization. But if I said write the linear factorization of this, this would be x plus 3 times x minus 2. That is the linear factorization. You have factors. They are linear factors because each variable is raised to the first power. The multiplicity could be higher. The multiplicity doesn't need to be linear. And then this one, the linear factorization here is going to be very similar. I'm actually just flipping the signs here because now my middle term needs to add up to -1. And we're going to do this with higher order polynomials. But again, just what the nice thing is when we have this as a linear factorization, look how easy it was for us to be able to find the zeros. Look how easy it is when we have something written as linear factors, not only to find the zeros, but to find the multiplicity. So linear factorization is very, very important, as well as being able to identify the multiplicity, or applying the multiplicity as well as the zero product property. So now what we're going to do is just kind of work on some problems that are in linear factor form and identify the multiplicity.